See if anyone's here. Okay. Just gonna wait for someone. If not, I'll get started. All right. Welcome back to STEM Online Academy. All right. So today is Friday. Friday is our office hours slash research problem night. Okay. So today we're going to be doing looking at integrals that researchers will truly find interesting in this area. Okay. So if you've ever wondered how to solve some impossible integrals, tonight is the night to look at these integrals. Okay. Whether you're an undergraduate or doesn't matter what it is, right? If you've encountered in one of your classes one of these really weird integrals and you don't know how to solve them, well, there's a few techniques that I can provide that will help you. Okay. And that's what we're going to be doing tonight. So if you've enjoyed, I don't know if any of you have also seen my past videos, my past live video. If you enjoyed Wednesday's session, okay, which was on complex logarithmic integrals and some other things too. What else were we doing? Complex logarithmic integrals and Feynman trick. Yes, we were talking about Feynman trick last time. Yeah, so yes, exactly, from Richard Feynman, who was a theoretical physicist. His method, he has some contributions in mathematics too, not just physics. He's mainly a physicist, but he had some interesting contributions in mathematics as well. So I talk about him because his trick for integration is really handy, especially when it comes to integrals that look almost impossible to integrate. Okay, so I talk about that as well. So we talked about Feynman trick last time, and we talked about complex logarithmic substitutions. All right. Now we're going to be inventing new specific functions tonight. It's going to take us much deeper into our adventure of integration. Okay. So yes, that's what we're going to be doing tonight. So it's a mixture of office hours. So anything you can ask me from the last video, either doesn't matter if you saw the live show and whether you're actually in the live show and you just want to ask questions on the last live show, or you missed it and you just watched it recently, and you've tried the homework question or whatever. Today is a good night. That's why it's called office hours. Office hours is exactly that, for you guys to come in and ask me questions of what we did the week of last Wednesday. Okay. And it's also not just that, we're also going to be looking at new integrals, new interesting integrals. So anyone who's in, whether you're from calculus all the way up to introductory graduate researcher, you may find these techniques very handy for your classes or your papers or whatever. Okay. All right. So we're going to be, as I said, we're going to connect the major pillars of advanced mathematics, at least when it comes to more specifically applied mathematics, because that's what I'm doing, right? So when it comes to applied mathematics, we're going to be merging a lot of the main pillars in that area. Okay. So one of them is going to be special functions. Okay. So we're going to go from special functions. All right. Then we're going to go to Fourier methods. Okay. And then residue calculus. Maybe not exactly in this live show, but what I mean is the last sequential live shows or videos that you've watched, you'll notice that I went from, it was Gaussian integrals, uh, uh, beta functions. So gamma function. Yeah, sorry, my mistake. Gamma function. We went from gamma function, beta function, and then we went to Gaussian integrals, Fourier. I think it was Fourier. Yeah, Fourier methods. So in Fourier methods, we went, and then special Fourier methods, residue calculus, and now special functions. Okay, special functions is going to require residue calculus and all of that, right? So contour integration, maybe even some Feynman trick and some other stuff. Okay, so yes, we're going to be looking into that today. So I hope you guys are excited for what's coming. Okay, so what we're going to do first, okay, I'm thinking special functions. So let's talk about special functions. Okay, so when it comes to special functions, you know, like the gamma function, the beta function, right? Stuff like that. We're going to be talking about that. Okay, so let me just pull up, actually, before pulling up a whiteboard, does anybody in the chat, just want to make sure everyone's in the right place and has some background. By the way, for my latest videos, it'll be handy if you have a strong foundation in linear algebra and integral calculus. Okay. But thumbs up in the chat, or even if not, if you're currently reading up on those subjects for A or B reason, it doesn't have to be for school. It can be maybe for self-interest. But thumbs up in the chat, please. Okay. Thumbs up in the chat. Ah, yes. Justin, thank you. I appreciate it. Can you tell me your background? What are you interested in? Are you interested in mathematics? You find specifically advanced mathematics? Who are you? Let me know. It would be appreciated. Any background in integral calculus, linear algebra? Undergraduate CS student taking multivariate right now, but I find any math interest. Ah, yes. If you're taking multivariable, yeah, you should be well equipped for what I'm going to do. Okay, that's good. I think you're just learning. You're interested in learning a new mathematical techniques. I'm supposing to help you with your courses, right? Especially with multivariable. This might be handy. Okay, so thank you. Yes, perfect. All right, so let's get to the whiteboard. Okay, there's a few things I'm going to discuss here, so I'm going to share screen. Okay, just give me a moment to share. Okay, we're going to go to the whiteboard. Okay, so as I said, it's a mixture for both. As I said, Wednesday, we talked about certain things. We talked about residue calculus as a way to calculate very hard integrals. It's a technique that can be very handy. And today, what we're going to do is a mixture of that, right? Special functions, residue, and Fourier transforms, okay? As well as being office hours for any previous students who watched my previous videos throughout the week and want to ask questions on the homework question. Okay. But since we have a new viewer here, I'm not going to go to the homework question yet. Okay, so this is part of the problem solving thing that I was doing, as you can see here. Right? I don't want to reveal that yet. We'll get to that soon. Okay. Okay, so just give me a moment. I think we're going to go to, we're going to go to talking about the gamma function and the beta function. Okay, for those if you don't know. So the gamma function, so the gamma function. I'm going to reiterate this. I've talked about this in one of my other videos, but it's so important, especially for undergraduates and for even researchers as well. Special functions are very, very important. Okay. Actually, I'll call this the special functions section. Then we'll get into it. Okay, so special functions. Special functions. Okay, and we'll get right into one, definition of the gamma function. Okay, so definition of the gamma function. Anyone can take a guess on what a gamma function is by any chance? Anybody at all? Anybody? Don't be shy. I just want to see what's in the chat. You're going to tell me what a gamma function is. Have you ever seen it? Have you ever heard of it? Comes up in statistics, or probability and statistics. Okay, I'll go through it right now, if that's handy. Okay, so the gamma function is this function right here. Okay, so a gamma function. So 1, it measures the following integral. Okay, so gamma as a function of n. Okay, so gamma as a function of n is equal to this improper interval, 0 to infinity, of x to the n minus 1 e to the negative x dx. Okay. So the definition of the gamma function. And when I'm talking about a gamma function, I'm talking about the integral form of it. Okay, so this is the integral form of a gamma function. Okay, all right. So any type of integral that is written as an improper integral of x raised to some exponent, okay, x raised to some exponent, so x raised to some exponent, times e to the negative x dx is a gamma function, okay? Just to mention that this is the integral part of the gamma function. So this is, note, this is the integral, right? The integral part, I'm going to put over here, integral part of the gamma function. The gamma function, okay? All right. All right, so this is one, the gamma function, okay? Anyone in the chat have questions? Yes, more general factorial, but I haven't worked with it at all. Okay, yes, I'm getting to your question. Yes, just another internet guy. Yeah. So the gamma function is related to a a factorial. I'm going to explain, right? So you have the gamma function when it comes to an integral form. Okay, that's why I put here, note, integral part of the gamma function. So I should say maybe this is like definition 1. Okay, definition 1 for a gamma function. Okay, now definition 2, very good question. Definition 2 is the following, that the gamma function of n is equal to n minus 1 factorial. Okay, so a gamma function is just taking your value, n is some value, okay, and taking that value minus 1 factorial. Okay, so it's related to factorials axes, right? So for instance, if you wanted to figure out the gamma of 1, well, this would just be 1 minus 1 factorial, which is just 0 factorial, which is just 1. Did I answer your question? Hope that helps. Or was that too fast? Oh, perfect. Yes. I hope you're seeing what it means with the factorials. Okay. So the gamma function is exactly that. It has to do, right? Has to do with factorials. Okay. So gamma of n. So if you want to calculate, and you can even find gamma functions of fractional values. Yes, you can find factorials of fractional values, right? So I just say definition 2. This is an example problem. Example. Okay, that's an example. Example 1. And if you did example, let's say example 2. Okay, if I want to find the gamma of 1/2, okay, now this is a little more tricky. You do need to know something here. Okay, you do need to know. So it generalizes the factorial out of it, of just the integer space. Yeah, exactly. Yes. It doesn't have to be an integer. It can be a rational number, right? Rational numbers are allowed to, what, right? So let me show you right here. So gamma of 1/2. If you calculate a gamma of 1/2, now here is the issue though. I do need to warn you of one thing, okay? If you calculated gamma of 1/2, remember it's n minus 1 factorial. So then if you did 1/2 minus 1 factorial, then you get a negative factorial, which is an issue, okay? All right, so there's a bit of an issue with that, okay? So what you would have to do, okay, if you want to calculate gamma of 1/2, okay, because you can see a negative factorial, you can't do that off the bat. That's a problem, okay? So what we would have to do, actually, and let's go back here, is we're going to use our integral. See this integral here, okay? This integral here that I've highlighted, okay? This integral here will help us calculate a gammas of, fractional values, if that makes sense, okay? So that's why I should be saying the gamma function, the integral part of it, of the gamma function, is not just, just to see, okay, that's how I can calculate a complicated integral, okay? But it also helps us get fractional values. For instance, if I calculated gamma of 1/2, right? So let's use, I'm going to use a blue here, actually, right? So let's use the integral, okay? So when I mean the integral, I mean this guy here, right? Gamma of n equals the integral from 0 to infinity of x to the n minus 1 e to the negative x dx, where n is 1/2, correct? So then the gamma of 1/2 equals integral from 0 to infinity of x to the negative 1/2, because I think we had a half here, right? N was a half. Yeah, so 1/2 minus 1, right? Right. So if you just tell this is 1/2 minus 1 e to the negative x dx, and then so forth. See what I mean? Okay. I hope that is sort of conceptualizing how to do this. Okay, perfect. I'm going to continue with the calculation of showing you how to calculate gamma of 1/2. Okay. Now, gamma of 1/2, we get this weird integral from 0 to infinity of x to the negative 1/2 e to the negative x dx. Okay. The thing is, though, this can be a bit annoying to integrate. I'm sure you would agree with me that we have a bit of a problem, right? How would we integrate this function, x negative half e to the negative x dx? Anyone have any ideas how to integrate this guy right here? Could be a bit of an issue, right? Because use substitutions won't work. For those of you who've taken integral calculus, you know that power rule doesn't work. That only works for a single powered function, x to the n plus 1 over n plus 1 plus c. It doesn't work. Use substitution doesn't work. Integration, well, I want to backtrack. Maybe use substitution. But integration by parts won't work. A lot of other things won't work. Okay, so anyone have any ideas of how to integrate this? Remember, this is a live show. I don't want to do all the talking. Anyone have ideas? Anybody have ideas? No ideas. Yeah, it looks tricky, doesn't it? Any ideas how to integrate x to the negative half e to the negative x dx? Okay, so we're going to use u substitution. Okay, but not in the way that you think. Quite often, a lot of you have been taught integration. I'm not saying not the right way. I'm saying an artificial way that is not helping you benefit whatsoever, right? Usually when we do u substitution, we find a u and we find a du. And we want our u, we want to choose a u such that our du pops up as some factor of dx, okay? If that makes sense. So we want to get the correct u such that I get my du to be correct, okay? Like right off the bat in one step. However, though, there are integrals sometimes that require multiple steps because it may not be obvious to figure out what the u function is. Okay. Guessing, but we can do yes. Oh, I didn't see what you said. Ah, yes. Oh, good. Two of you are. Yeah. So I'll get to you in a sec, Locus Curia. Polar coordinates will come in handy at some point. You're right. Just another internet guy. Yeah, I know what you mean. X equals u squared. Oh, yeah, you got it. Yes. How did you know? Oh, good. Yes, x equals u squared. Perfect. Excellent. Yes, so x equals u squared. So x equals u squared. That's right on the bat, right? Now, I'm glad you saw that. That's very good. Now from this, I should take maybe x to the 1/2 equals u at some point. When is this important? When should I do that? That x to the 1/2 equals u. Or should I just go directly and just do dx equals 2u du? I like when you guys are, engaging. Okay, so I do x equals u squared and then do directly to the differential dx equals 2u du. Okay, modulus. Yeah, I know what you mean. Locus Curia. Yes. Yeah. At some point, there'll be some type of modulus coming into it. Yeah, if you mean like with, well, there's going to be Gaussian integral. It could be. I think. Yeah, it looks like it will be a Gaussian integral at some point because we'd have to do that. But yeah, we're getting right to it. Okay, so x equals u squared. Okay, dx equals 2u du. Okay, that means that if I want to solve, if I want to solve for dx, so my dx I want to replace with a du, right? I want my x's to replace with u's. So we're going to do that right now, right? So substituting all of this in, we get integral, right? Now, what are my limits of integration here, by the way, if I put everything in terms of u? What are my limits of integration? First off, if it's in terms of u. Come on, guys, let me know. What are my limits of integration? Limits of integration, what are they? If x is equal to u squared, I'll put everything in, right? So x is equal to u squared, so u squared all to the power of negative 1/2 e to the, well, x is going to be negative u squared, okay? Dx is going to be 2u du, okay? Very straightforward, all right? But what are my limits of integration? It needs to be in terms of u. Yes. Yes, but how do you know that? How do you know it's from 0 to infinity? Can you justify that? It's one thing to know it, but when it comes to my live lessons, I want to make sure that you're understanding why. Why is it from 0 to infinity? Anyone know why it's from 0 to infinity? Yeah, exactly, right? You just substitute into, if you know x equals u squared, right? And you know your x is going from 0 to infinity, right? So let's see, 0, x is 0, u is 0. Okay, that's the lower bound. Okay, upper bound, x is infinity, u squared is infinity, take the square root of infinity. Right? Very straightforward. Okay, so 0 to infinity. Now, we have everything in terms of u. We replaced x in terms of u. Okay, so now we've got this. Now we can clean this up, integral from 0 to infinity, right? This becomes u to the negative 1, e to the negative u squared of 2u du, okay? I love the gamma function. It's one of my favorite special functions, by the way. So integral from 0 to infinity, okay? U to the negative 1 times 2u, well, this cancels, right? U's cancel. I'm left with twice e to the negative u squared du. Okay, and I can pull the constant out twice. The integral from 0 to infinity of e to the negative u squared du. So what's his name was correct. It looks like it's a Gaussian integral of some sort. Yes, I'm getting to that in one moment. Yeah. Potato 8386, I believe. X is 0, u squared is 0. Yes, x is infinity, u squared. Yeah, of course. Yes, yeah, you're both right. That's why I have those limits of integration for you, going from lower limits from 0 to infinity. Now you'll notice, what's his name? Lopez Carrillo was right. Polar coordinates are needed for this integral right here. Why is polar coordinates needed for this integral? If any of you know. I mean, not everyone knows what a Gaussian integral is until they've got into multivariable calculus, at least multivariable calculus, and even that's near the end of multivariable calculus. Anyone know how this relates to a Gaussian? Just let me know. Anyone know how this relates to a Gaussian integral? Anybody? Come on, guys. Don't let me hang in here. Okay, I'm going to help you guys here. This, twice the integral from 0 to infinity, is equivalent to saying the integral from minus infinity to infinity of e to the negative u squared du, right? Okay. I can write 2 times the improper integral of e to the negative u squared du as the integral from minus infinity to infinity of e to the negative u squared du, right? Because that is just an integral property, right? From minus infinity to infinity. Okay. Any questions on that? I'll make sure you guys. Yeah, exactly. Symmetry. Yes, potato. Okay, good. So let's get back to it. So now that we've got that, yes, by symmetry methods. Now you'll notice right here, as one of our other viewers has said, that this is a Gaussian integral. Okay. Do you guys know what I mean by that? What is this equal to? What is it equal to, and how do we know it's equal to that number specifically? Okay, so you guys, I'm assuming you guys have no idea. It looks like Potato has no idea. Okay, I'm going to show you how to do this. Anytime, I'm going to move over here. I'm going to need another, I need another page. Just give me a moment. Yeah, new page, possible. Yeah, so we're continuing. So continuing, right? So continuing. Just 1 second. Continuing. Okay. By definition, yes, by definition, I'm going to write over here. There's a definition I need to talk about. For those of you in multivariable calculus, you're going to learn this at some point, or if you've taken introductory probability statistics and mathematical statistics and probability, you'll know what I'm talking about here. Definition: anytime you see I, so the integral I, I'm going to call it. So I is an integral. Okay, I equals the integral from minus infinity to infinity of e to the negative x squared dx. Okay, this integral here, if you've already noticed, can't be integrated by standard methods. In other words, normally if you have a function e raised to a function, okay, you would use u substitution and so forth and get a correct differential, right? So for those of you who remember, the integral of e to the u du, sorry, wish my writing was better on this, e to the u du is equal to e to the u plus an arbitrary constant, okay? That's just an indefinite integral definition of e to the u, right? However, we can't use that here because we don't have a correct u in order to get the correct differential in order to integrate, okay? Yes, I'm about to verify that. Don't worry, I'm getting to that. Yeah, about to verify that. So what we do is, since we can't integrate this by normal methods, we use something called a Gaussian integral. This is a Gaussian integral. Okay, so this is called a Gaussian integral. Okay, and it's always equal to square root of pi. Well, not always square root of pi. It's to be some factor of square root of pi. It depends on what the constant is here. Okay, if it was negative 2x squared and 3x squared, it will have different variations of root pi, maybe root pi over 2, maybe root pi, whatever. But yeah, a standard integral from minus infinity to infinity of e to the negative x squared dx is root pi. Okay, and the way we do that is we translate. Okay, so here's the methodology. We translate the polar coordinates. Okay, translate, sorry about that. Translate to polar. Okay, so translate, step 1. So step 1, translate to polar coordinates. Polar coordinates for our integral. Okay, anyone know how to do that? Anyone know how to do polar coordinates of the integral? Okay, anyone know? Let me know. Anyone know what it is? If not, I'm going to go through it. Okay, so what we're going to do here is we take this. We take I. Okay, so we take I again. Right, so remember, I was equal to integral from minus infinity to infinity of e to the negative x squared. Okay. Now, what I need to do is I have to split this up. Okay. What I mean by that is if I is equal to integral from minus infinity to infinity of e to the negative x squared, and I'm going to use another I, and I, define I equal to this, I equal to integral from minus infinity to infinity of e to the negative y squared. This is respect to x. This will be respect to y. Okay. dy. Okay. If I multiply them together, I squared is equal to I by I, which is equal to the integral from minus infinity to infinity of e to the negative x squared dx times integral from minus infinity to infinity of e to the negative y squared dy. And then this is just I squared equals integral from minus infinity to infinity of e to the negative parentheses x squared plus y squared. Right? See what I mean? Yeah. Yeah, we're getting to that. Yes. Yeah, we're getting to that. Okay, good. You didn't know how we get the r from x since r is, but yeah, watch what happens, right? There's a reason why I did that, right? Right, because by defining I in terms of x and I in terms of y, they're both similar. Multiply them together, I can add their exponents, right? And then this I squared can now be written I squared equals the double integral. Okay, this is in polar now of e to the negative r squared. Okay, e negative r squared because x squared plus y squared. If that makes sense. So e to the negative r squared, r dr d theta. This, by the way, is a Jacobian factor. Okay, r dr d theta is a Jacobian factor. Those of you who know what a Jacobian is you take the determinant of each of the mixed partial derivatives in terms of r theta and stuff like that. Okay, I should actually put this maybe in a different color to highlight. This is my double polar form here. E to the negative r squared. Sorry about that. Just give me a moment. E negative r squared r d theta. I want to highlight that this is a different integral. R d theta. Okay. Now, this is in polar. What's the limits of integration be? How can we determine that? No limits of integration, guys. Come on. Limits of integration. Well, first off, e to the negative r squared. I need to mention something here that's very important. in order to figure out the limits of integration, you need to know how your function looks like. So for instance, if I go to the graph over here, okay, I'm going to make a graph here. Okay. The function we're looking at is e to the negative r squared. Okay, so we have some function of r, f as a function of r. That's what's changing. R is the independent variable, f of r is the dependent, right? E to the negative r squared is a bell curve. A bell curve, something like this, right? So f of I equals e to the negative I squared. Okay, does that make sense? It's from 0 to 2 pi over 2 because it's only in the first quadrant. Just another, yeah. Yes. So for both, just another inner guy. Yeah, I know what you mean. Outers from 0 to pi over 2. Yeah, and it's only because it's in the first because it's only in the first quadrant. You said. What's in the first quadrant? What are you talking about with respect to what's in the first quadrant? What function? Potato. Yes, potato. Initially, our original function was from minus infinity to infinity. Minus infinity to infinity, right? The original function was from minus infinity to infinity, right? Of e to the negative x squared plus y squared. Then I translated that to e to the negative r squared, and then I put it in polar because in terms of everything was x squared plus y squared, so we translated to polar. Now we're finding new limits of integration. Just another inner guy, like it's greater than 0. Yeah, we're getting to that. Okay. So this right here, okay, this over here, the limits of integration, okay, should be the inner limits of integration, okay, should be from 0 to infinity. Okay. How do I know it's from 0 to infinity? How do I know that? How do I know I'm going from 0 to infinity for the bound here? Lower limit of integration is 0. Upper limit of integration is infinity. Why is that? Why am I going from 0 to infinity? So it's not minus infinity to infinity. No. Right, potato? 0 to infinity. The thing, I think you're getting confused with the bell curve. Okay, yes, you're seeing that it's transposing here from minus infinity to infinity. Okay. However, though, you need to think about it in two ways. If I were integrating from minus infinity to infinity, my whole integral would collapse, right? If I were to do that, if I found the area of this whole thing, because that's what we're doing, if you're saying from minus infinity to infinity, this would not exist. Okay, if I went from minus infinity to infinity, the whole integral will collapse. Why would it collapse, though? How do I know it's going to collapse if I went from minus infinity to infinity of the bell curve function e to the negative r squared? It's simple, right? If I put minus infinity to infinity, e to the negative infinity, that would be approaching 0. E to the infinity would be approaching infinite. And then that means that this entire integral will be undefined. That wouldn't make sense. Okay, so if you go from minus infinity to infinity, if you were to calculate the area under this would give you an infinite area. And that's a big mistake, okay? It's a bit counterintuitive, actually, because normally when we do integration, when we see an area, we have a curve, and we see that we want to calculate the area based on how our drawing is. We say, okay, we calculate from this point of the interval to the other point of the interval. Here, from minus infinity to infinity, you don't want to do that. You're going to have a serious problem. Okay. Yeah, that's why I wanted to correct. I wanted to correct you for a second there. I'm about to get to that. Yeah. Limits were 0 to infinity, and r is, what is the name of this? Yes, 0 and max at infinity. Yeah, yes. I think I'm understanding what you're saying. I'm about to write exactly that. Watch what happens. This integral right here. Okay, so it goes from 0 to infinity, right? I hope you can agree on that. Now, the outer limit of integration with respect to theta, since we're dealing with x squared plus y squared, by the way, when doing any type of double integral, always do it in Cartesian coordinates, because then you can see in a two-dimensional geometry how it's working and the limits of integration will be, right? This should be a whole circle, okay? Because we're dealing with x squared plus y squared. X squared plus y squared is a whole circle. So the limits of integration would be, well, r, as we said, r was going from 0 to infinity, right? So including, so that's 1 second, 0 small equal to r smaller than infinity. Theta is going from 0 smaller equal to 2 pi, because this is the entire circumference of a circle. Circle has 360 degrees, right? So 0 to 2 pi radians, okay? So limit of integration on the outside would be 0 to 2 pi. Does that make sense? I hope that answers the question, right? So yeah, it's going from 0 to 2 pi. Okay. Okay, so just another guy got it. Potato, potato. I hope you are understanding. Okay. Yeah. So this type of integral is slightly counterintuitive, if you understand what I mean, right? So you have to, that's why I put that definition up, because if you haven't seen the definition for a Gaussian integral, you would have no way of knowing how to do this, right? You just assume, how am I going to integrate e to the negative x squared, right? But yeah, this is the way to do it, polar coordinates, right? So in polar coordinates, we transpose into the new limits of integration, okay? Then from here now, okay, I have that. I can evaluate I squared equals integral from 0 to pi, right? And I'm going to use Fubini's theorem, if that makes sense. What that means is integral from 0 to 2 pi can be written like this. Integral from 0 to 2 pi with respect to theta, where I can pull in the differential here, multiplied by the integral from 0 to infinity of e to the negative r squared. Sorry about that. R squared r dr. Okay, this is by Fubini's theorem. If those of you who know who Fubini is, so by Fubini's theorem. By Fubini's theorem. Fubini's theorem on double integrals. Does that make sense? Okay. So we've got that. All right. Now we can do this easily. Okay. I squared can be calculated as follows. Okay. So it doesn't matter the order. I'm just going to do it like this. So I'm just going to leave this the way it is for now. This is a very easy one, but this watch what happens. I'm going to calculate this by using u substitution, right? E to the negative r squared r dr. Very easy to use u substitution. Actually, I'll do the u sub here before I do the integral. Okay, so let u, what should my u be for the u substitution of this integral here? Let's say the u substitution be for this integral here. What should it be? Anyone know? Integral of e to the negative r squared r dr. What's the u substitution? Yes, excellent, guys. Potato, potato, and just another guy got it correct. Yeah, negative r squared. That would be the correct u. Negative r squared. Okay. Reason for that is because you want to make sure you get your correct du. Actually, though, I want to make a slight correction. Okay. R squared. Okay. R squared will be the correct u. Okay. All right. Because if I use u equals r squared as opposed to negative, I mean, this doesn't make any complications down the road when we integrate, right? If I use negative r squared, actually, would that give us an issue? If it would. I actually have to think about that. Use r squared. Substitute that in for u equals negative r squared. Yeah, u negative 2u du negative. That should be fine either way. Negative r squared. Multiply the same thing. Yeah, it should be fine the same way. Okay, let's use the negative r squared that you said. Yes, and then we'll do du. The differential has to be minus 2r dr. Okay, because that's the differential of u. The point of this here, okay, is just to make sure that we have the correct u being r squared, du's 2r dr. We take care of this part. We can replace the r's with the u's, the du's with the drs, right? And then what I can do here is I want to divide by negative 1 over 2 du to get that factor of r dr, right? R dr can be replaced in terms of du now, okay? So now we're going to substitute in. So substitute. We're going to substitute back into our integral that we were dealing with upstairs, I squared. I squared was the integral from 0 to 2 pi of d theta times the integral from 0 to infinity. E to the negative r squared dr can be replaced, right? So now it's going to be integral. Might use a different color for that, otherwise it gets confusing. Integral from, you can tell me what the limits of integration are. In the meantime, I'll put this in. E to the negative r squared, so e to the negative, oh yeah, r squared. We used u was negative r squared. Yeah, so e to the u, okay. R dr was the negative 1/2 du that gets substituted in, okay, because that's the r dr. What are my limits of integration? Yes. Yeah, the negative. Yeah, exactly. Yeah, that's right. Yeah, exactly. Yeah, I'd love to do that. Yeah, so this would be I squared. Yeah, you can do that, right? So that'll just be like integral. And it doesn't matter because integration is commutative. So if I want to put it over here, I could put it over here or over here, the negative. It doesn't matter. So minus integral 0 to 2 pi of d theta times integral negative 1/2. So put negative 1/2 on the outside. Yeah, negative 1/2 of that, integral 0 to 2 pi d theta, integral of e to the u du, right? Okay. What are my limits of integration for the u, though? Yeah, it's still 0 to infinity if you substitute back into u, right? If you had u being 0, r is 0, u is infinity. Yeah, exactly, 0 to infinity. Yep. I always like to ask people what the limits of integration are because they're not always the same. It depends what they initially were in the original variable, but when you translate it into u, it may be different, but here it's the same. Okay, upper and lower limits. Okay, now we've got this. So I squared is minus 1/2 integral from 0 to 2 pi of d theta times integral of e to the u du. Now this part here, integral of e to the u du, this is just multiplied by e to the u from 0 to infinity. Okay. Right. By the way, I like to write it like this. It doesn't matter. I'm sure a lot of you have seen it in your textbooks or something. Limit as t approaches infinity. T would be my dummy variable of the integral from 0 to t of e to the u du. It doesn't matter. I could have said the boundary from 0 to infinity, but quite often it's more precise to write it as the limit as t, or limit as something approaches infinity, because you can never equal infinity, you only approach it. Okay, so we have that. Oh, wait. You said negative infinity. Say u equals negative r squared, you have to use negative as the upper bound. Yeah. Oh, yeah. Yes. Did I not see that? Yes. Yes, both of you are right. Thanks for catching the mistake. Yeah. That's why at the beginning I was sort of intuitively saying to myself, we have to use u equals r squared. Yeah. Yes. Because if we were to take the square root at the very end of the day of this negative, we'd have a problem. We're not in the complex numbers, we're in the reals. Yeah. R squared. Yeah, sorry about that. I appreciate that. Yeah, r squared. Negative, bye-bye. I have to get rid of the negatives now. Yeah. Yeah, that was the reasoning that I was forgetting about, because the I squared. Yeah, yeah. 1/2. Let me be careful here. There was a negative here. We said, yeah, get rid of the negative. Okay. Hope that answers. Yeah, exactly. Yeah, that's why intuitively at the beginning I was thinking of using the r squared, because otherwise you'd be in the complex. That'll be a problem. Square root of -1 can't do it here. We want to be in the reals. Okay, so we've got this right now. Thank you guys for noticing that. So we've got this integral right here. Okay, let's evaluate this integral. I like using different colors. Okay, so we got I squared. I squared is equal to 1/2 the integral from 0 to pi. I don't know why I still have that up. That should just be theta from 0 to 2 pi divided by 2. We'll take care of that. Over here now we have the limit as t approaches infinity. This integral here is just e to the u, right? E to the u. E to the u from 0 to t, right? Very straightforward. And I squared, actually I'll evaluate that right now. That's just 1/2. 1/2 times theta from 0 to 2 pi. Okay, and then take the limit as t approaches infinity of e to the u, or e to the u. Now e to the u, that's just going to be e to the t. What was that? Oh, that should have been e to the negative u. Yeah, because I put the negative, not the negative now, negative. Yeah, because that little negative, I almost forgot about it. Yeah. So you have to be careful. One little mistake and everything just gets annoying, right? So you have to be careful with mathematics. Okay, so e to the negative u. E to the negative u. Okay, so e to the negative t. I'm going to put square brackets here because we're going to be subtracting upper and lower limit of integration from fundamental theorem of calculus, right? So e to the negative t minus e to the 0, right? Like this. I think there's no dispute on that. Okay, and then from this point on, I squared, we can start inputting this. We know that 2 pi divided by 2 would be pi. Okay, so this is pi multiplied by the limit as t approaches infinity. Well, first off, let me just write that in. Limit as t approaches positive infinity. E to the negative infinity. What happens to that? What happens to e to the negative infinity here? Remember, e to the negative t, we can figure out its behavior by drawing a exponential decay function. Okay, so like this. What is happening as t approaches infinity? Anybody know what's happening to e to the negative t as t approaches infinity? Anybody know? Come on, guys. E to the negative t, right? So look at this guy. So as t approaches infinity, right? Anybody know? Anybody at all? Yeah, of course it approaches 0. And the reason why is because it's an exponential decay function, right? So as t approaches infinity, you can see that e negative t approaches 0. Then e negative t has to approach 0. Okay. All right, so this becomes 0 minus 1. Let me see here. That should be minus because of the e to the negative u. So that should have been plus. Yeah, that should have been plus somewhere. Yeah, it should have been plus. Did I forget something? This should have been plus. U negative u. U was equal to r squared. U, yes, u is negative is r squared. Yeah, that's negative u. I integrate e negative u. After integrating e negative, yeah, because there's a negative here. Yeah, so this is actually a negative. Yeah, negative. Then this is going to be like that. Okay, so -1 times -pi, right, is just pi, right? I squared is pi, correct? Right? So I squared is pi. Therefore, if I squared is pi on the next page, if we have room, if you guys can read it better, no, I was another page here. I squared is equal to pi. So we're getting I squared, because initially we had I squared equals negative pi times negative 1. And then this gave us pi for I squared. Therefore, I is equal to root pi. Okay. And because I is equal to the integral, right, from what we said earlier, which was minus infinity to infinity of e to the negative x squared dx, which was equal to our polar coordinate integral. And we know that polar coordinate double integral is equal to root pi, then this is equal to root pi. And that's how you verify the result, okay? Any questions? Yeah, it's the same. Yeah, thank you, Potato. I appreciate it. But yeah, exactly. Yeah, exactly. It's just by symmetry, and then after from that, it's not that complicated actually. I mean, at first, if you don't know what a Gaussian integral is, it looks complicated. But if you relate, as long as you have, you have that background when it comes to integration, then it's not going to be complicated. I show you the definitions, and you can be able to link things together, right? So yeah, okay. So that's a bit about the gamma function. Oh, there's one more thing about the gamma function I wanted to mention, right? We're talking about that integral there, okay? So I squared I equal root pi, okay? And we figured out that that's the case. Now, how does this relate to gamma? And that's initially we were solving a gamma function, right? Right. If you remember. Okay, we had an integral from 0 to infinity of x to negative half e to negative x dx. We reduced it down to e to the negative u squared du. Well, that's automatically equal to root pi. Okay, if you're following from earlier, because this was part of the gamma function, it came out to be a Gaussian integral. This was equal to root pi. And then from there, that means if the Gaussian integral is equal to root pi, then gamma of 1/2 is root pi. Okay, so I shouldn't say I'm completely done. Therefore, thus, the gamma of 1/2 is equal to root pi. And that's always true. That's a fact. Okay, so gamma of 1/2 is equal to root pi. Any dispute on that? So that's how the Gaussian is equivalent. Well, how the Gaussian is related to the gamma function. Okay. Now, one more thing about the gamma function is I want you guys to be able. Oh yes, thank you, just another guy. I appreciate it. Yes, hope you're learning a lot. Okay, good. All right, so yes, so we have our gamma function of our fraction here is equal to root pi. Now, as I mentioned, the gamma function can be used to calculate any number, a rational or integer. So as I said, integers, obviously integers, 1, 2, 3, so forth. Rational numbers, that means like fractions like this, 1/2, 3/2, and so forth. Now, you may be thinking, wait a minute, what if I don't want to calculate gamma of 3/2 and do all this craziness, right? Go through the improper gamma integral, right, that I showed you earlier, this guy over here, and then do 3/2 minus 1 and do all that. Okay, what you can do is use another definition of the gamma function. I showed you two definitions, the improper one and the regular gamma relationship with fractional values, factorial values, right? To calculate fractional values, if you don't want to use the gamma function directly, do this instead. There's another definition. Definition 3. Definition, I should use a different color here. Definition 3. Definition 3 is the following, okay? That the gamma, if you take the gamma function, sorry, I'll write like this. If you take n gamma of n is equal to gamma of n plus 1. This can help calculate, right? Helps calculate fractional values as well, not just that improper integral, fractional values. Any questions on that? Sorry for that. Oh. Okay, good. Thank you. I hope that makes sense, right? So this is another way to calculate fractional values of the gamma function. Let me explain. So we calculated gamma of 1/2 as root pi. Let's say we want to calculate, I'll give you an example, gamma of 3/2. So example, okay? If I want to calculate, I like using different colors. I'm obsessed with using different colors for some reason. I feel like it gets boring after a while. If you want to calculate example 2, for instance. Calculate, okay, so let's see, you want to calculate. I want to calculate gamma of 3/2. Okay, so I want to calculate gamma of 3/2. Okay, I can use this new definition. All right, and the way I do that is just using definition 3. So if I want to calculate gamma function of 3/2, then this is just the gamma function. So gamma of 3/2 plus 1, right? Well, the n is 3/2, right? 3/2 plus 1. Oh, wait a minute. I'm using it wrong. Sorry about that. My mistake. So gamma of 3/2, right? Okay, so if gamma of 3/2 is actually equivalent to something interesting here. Gamma of 3/2. Use the left-hand side. That's what I mean. Take n gamma of n. If n is equal to 3/2, right? So n here is 3/2, okay? So what that means is if I use the definition above, it becomes gamma of 1/2 plus 1. In other words, here, sorry, this is what I'm talking about. N is this. This is my n. N is equal to 1/2. Okay? In other words, you need to take definition 3 and extrapolate it, split it up. N times gamma of n equals gamma of n plus 1, where n is not what you have here. That's not your n. Your n is what you split up of your actual number. So plus 1, right? So 1/2 plus 1 will give you 3/2. So n is 1/2. And then what you would do here is you take n gamma of n, right? So we now know what n is. So take 1/2 times gamma of 1/2. Okay, so 1/2 gamma times 1/2 of gamma times 1/2. Gamma of 1/2. Does that make sense? Yeah, exactly. Yes, I was just putting that right down. 1/2 gamma of 1/2, right? And we know what gamma of 1/2 is. That's why I calculated it earlier, is root pi. So this becomes root pi over 2. So gamma of 3/2 is root pi over 2. Okay. So finding, in other words, you can also relate this to factorials. If you want to calculate 3/2 factorial, it will be root pi over 2, right? Because gamma is related to that. Does that make sense? Hope that makes sense. Okay, so that's another way to calculate more and more gamma functions. Okay, gamma values, right? 1/2 factorial, 3/2 factorial, 5/2 factorial, doesn't matter. Okay. All right, let's go to the next special function, the beta function. It's beta function day. Yay. Beta function. Beta function. Okay. This is the special function number 2. So this is going to be special function number 2. Function number 2. Okay. All right. Hope you're enjoying it. Okay, so we're now moving to the beta function. The beta function has to do with the gamma function to some degree. I'm going to talk about some properties here. First off is the integral, okay? So the integral property, so definition one, when it comes to the beta function is that if you take the beta function, okay, so if you take the beta function, okay, so let's say you have beta as a function of x comma y, okay, this is automatically equal to the integral from 0. I like when my integrals look like stretched s's, because it is a stretched s, right? An integral is actually a stretched s, and that's equivalent to the limit of a summation. That's what an integral is, first off. But anyways, I'm getting off topic. Yeah, so integral from 0 to 1 of t to the x minus 1 power times 1 minus t to the y minus 1, where x and y are exponents. Okay. All right, so we've got that. T to the x minus 1 times 1 minus t to the y minus 1. This is called the beta function. Okay, so this is the beta function. Beta function. Beta function. Integral, I should say, to be more precise. Integral. Okay, this will be handy actually, because a lot of times you guys, especially for those of you who've taken calculus 1 in university, have seen integrals like this. You have some integral of some variable raised to a power multiplied by 1 minus that variable to another power. Now, that being said, though, you can't always apply this integral to those types of integrals, because the limits of integration have to be from 0 to 1. So lower bound 0, upper bound has to be 1. Okay. So that's the first thing here. All right. So we've got that. So this is the beta function when it comes to an integral. Okay, I'm going to explain a bit more. So yes, we've got that. Now, definition 2 for a beta function. Okay, so that's definition. Definition 2 is the following. Okay, and it states that if you take, this is an identity property. Okay, so this is not exactly the same thing. This is an identity. So the identity property, I should say beta identity property, beta identity property is the following, and you can calculate it doing this, right? So the beta function is also equivalent by taking beta of x comma y, which is equal to, we'll put over here, the gamma function of x times the gamma function of y divided by gamma function of x plus y. Okay, this is a way to calculate the beta function as well. You can also do it this way. Quite often, you can compare your answers, actually. Let's say you calculated the integral, you're going to get a value because it's a definite integral. That's what a beta function is. You get some value, maybe it's 1/2. Your beta identity property also has to be 1/2. If one or the other isn't the same, then there's an inconsistency because they're both the beta function. Does that make sense? Okay, so that's what we've got right now. So the beta identity property. Okay, let me see if there's any other integrals at the moment. There's another beta integral. I'm not going to talk about that because I want to move to other topics. I'm just giving you the basic lowdown of how the beta function is, a special function. Okay, so that's definition 1, definition 2. Let's look at an example. Okay, so let's say if you want to calculate, if I want to calculate the integral, say I want to calculate integral from 0 to 1 of, let's say, x cubed of 1 minus x all to the power of 2 dx. Okay. How would I calculate that? I have to show you, actually. It may not be from it may be a little bit weird not doing it without seeing me do it. Okay, so remember, we're calculating this integral right here, right? We're calculating the integral from 0 to 1 of x squared. Okay, so we have x squared, x cubed times 1 minus x. Okay, we want to calculate this. Now, the way we do it, we actually have to use the beta identity property. Okay. So what I mean is we use definition 2 to calculate what this is, to calculate what our integral is. As long as we know x and y. X and y are the exponents, depending what our exponents are. So we have to determine what our exponents are. So what you do is you let x minus 1 equal 3. Okay. X minus 1 is 3, right? Because on the left-hand side, I in the definition of the beta function, x minus 1 was our variable. I'm going to use a different variable. I might use t minus s and t because I already have x's here. So let s minus 1 equal 3. Okay, and I'm going to let t minus 1 equal to 2, if that makes sense. Yeah, exactly. Yes. Yeah. Yes, very good, guys. That's right. Yeah, exactly. You're way ahead of me. So that's, yeah, because we're going to solve for s, 3 and 1. This will be 4. T is going to be equal to 1 and 2. T is 3. Calculate, I have s and t as my variables here. So I can now calculate what my beta function is. This is going to be x of beta. Beta as a function of s and t is this exactly that, right? Gamma of s, gamma of t, divided by gamma of s plus t. Okay, and you can see here that the beta function of 4 comma 3 would be equivalent to the gamma of 4. Yeah, gamma 4, gamma of 3 over gamma of 7. Can you guys tell me what the gamma of 4, gamma of 3, and gamma of 7 is? Oh, yeah, 1 over 14. Yes, but I didn't see that. Yes, that should be it, because what you get here is just 4 minus 1 factorial. Then you get 3 minus 1 factorial, and then you get over here 7 minus 1 factorial, right? 4 and 1 is going to give you 3 factorial, 2 factorial, 6 factorial, and that's just 3 by 2 by 1, right? This is just 2 by 1. This is just 6 by 5 by 4 by 3, 3 by 2 by 1. Yeah, it should be 1 over 14, I believe. Yes, it is. I think it is. Yeah, 1 over 14. Okay, so that is a beta integral. I have one more for you guys to do. Okay, one more beta function integral. Let's do this one. Okay, calculate this guy now. Okay, so calculate. Let's say I, your integral. Okay, I is equal to the integral from 0 to 1 of, let's say, let me think. I is equal to, let's say W to the W to the 1 over 2. Okay, so W to the 1 over 2 power times 1 minus W to the second power dW. Looks like an omega, but try calculating that one. Oh, 1 over 60. Oh, damn it. Yes, I sort of rushed through. I was assuming one of you guys were correct. Yeah, n minus 1 factorial. Going back, 3 by 2 by 1, 6 to use 12, 6 by 5, 30 by 4, 30 by 4, 120, 120, 3, 360, by 2, 7, 20. Yeah, so you 1 over 60. Yeah, so you 1 over 60. Yeah. Yeah. That's to clarify. Yeah, I rushed that calculation myself. I assumed you guys already just did it really fast. Okay, but yes, that's correct. Okay, I have one more integral for you guys to do. I'll be right back. I have to use the washroom. Okay, so I'll be right back. Try doing this integral right now. W to the 1/2. I'm going to make this 1 minus w to the 1/2 as well. Okay, I'll be right back. Just have to guess. All right, guys, I am back. Just want to make sure you guys are okay. Perfect. Let's see. One of you've calculated, I believe, the new integrals. That pi over 8 related to the new integral, I'm assuming. So let's 1/2. Let's say we have here. Doesn't matter what I call it. I'm going to call it m and n. M minus 1 equals 1/2. Therefore, the m is going to be 3 3/2. And let's say n minus 1 is equal to 1/2. Yeah, n is 3/2. Yeah, so then you just get beta of 3/2 and 3/2. Is it? Yeah, so then it's going to be gamma of 3/2, gamma of 3/2 again. It's gamma of 3/2 divided by gamma of 3/2 plus 3/2, and that just gives us gamma of 3/2 by 3/2. We'll put that in a sec. 3/2, 3/2, 6, 2, 3 gamma of 3. So this is gamma of 3. And then this is going to be equivalent. Gamma of 3/2, I think we said was root pi over 2, I believe. Root pi. Yeah, it was like root pi over 2. Pi over 2 times root pi over 2. Gamma of 3/2 would have been 3 minus 1 factorial is 2. 2 factorial is 2. That's root pi over 4 divided by, yeah, so root pi over 8. Yep. Yes. Oh, I think it was pi over 8. Yes, pi over 8. Yeah, because square root pi over 8. Yeah. Okay, so that's what my integral would have been. Perfect. Excellent. So we've covered the gamma function. We've covered special functions. Another thing I want to discuss here, I'm going to pull it up, that you guys may find interesting. I wanted to pull this up as well in this live session. No, that wasn't it. I was looking at another mathematical method from my book that I wanted to talk about. It was what was it again? I think we were going to talk about not you. Yeah. I want to discuss something called Feynman trick. Do any of you know what Feynman trick is? Any of you know at all what a Feynman trick is? Let me know in the chat, any of you guys to know what Feynman trick is. Yes. Yes, just another internet guy, differentiating under the integral. Yes, I assume just another internet guy has quite a bit of math background. Yes, that's correct. Differentiate under the integral. We're going to look at that in a moment. Okay. A trick for Potato says a trick for physics because he was a physicist. Yes, he was. Feynman was a physicist, but he also has a contribution in mathematics too, though. And his contribution is to calculate exactly what just another internet guy says. It's a way to calculate complex integrals, differentiating under an integral sign. So let me just remind you, for those of you who don't know, how this works. Okay, so pretty quickly, we're going to talk about Feynman trick. Okay, so Feynman trick. I like when my letters are better for some reason. Trick. Okay, so we've got the following, right? So here's a definition. Okay, here's a definition. Is that you have an integral. Okay, so what you do for Feynman trick is the following. Okay, Feynman trick states, the following. Define a parameter. Yeah, define a parameter called, doesn't matter what we call it. I'm going to call it little alpha. Okay, so we're going to define a parameter. I'm going to call it alpha. All right. Then we differentiate with respect to the parameter. With respect to that parameter, to that parameter of both sides of the integral, of both sides of the integral of the integral. Okay, and our integral usually looks like this. So here's the formality of it. Okay, so formal definition. Okay, if everyone is following along. Okay, so formal definition is this. Okay, so if you have I, right? So I is going to be defined as an integral, and this integral will be equivalent to the following integral from, let's say, x0 to x1, or limits of integration of a function of f in terms of x and alpha. Okay, so x and alpha dx. Okay, I should say I is a function of alpha. Right? So I is a function of alpha now. Okay. So in other words, we have a function. Initially, our integral is a function of x. All right. Let's say we don't know how to integrate that function. Okay, using elementary methods don't work. We use something called Feynman trick, which allows us to input a parameter. Let's say I call it alpha, right? And you want to input your alpha in the right position of your function such that when you differentiate both sides of the integral, after you've simplified it, it's easier to integrate. Okay, so that's the formal. And then here's definition 2, right? So definition 2. So let me just show you what that means mathematically as opposed to words. Okay, so definition number 2. Okay, so that's the Feynman trick. I'm going to say here's this Feynman trick. Okay, so that's Feynman trick by definition 1. And then definition 2 is just differentiating on the integral sign. So, right, so this is just differentiating under integral sign. Differentiating under the integral. Okay, under the integral. Okay, so we're doing it like this. Let me know if you have any questions. Okay, so far, no. Everyone's on point here, I hope. So what we do is, as I mentioned, differentiating on the integral sign will just give us this, right? So it's just going to give us, we'll imply that d alpha, right? I'm differentiating both sides with respect to the parameter alpha. So d alpha, right? The derivative with respect to alpha is equal to d by d alpha of the integral, okay? Of the integral from x0 to x1 of f of x comma alpha dx. Okay, that's a dx. Sorry, I write fast. Dx. Okay. And this can also be written, if you want to be more precise, integral from x0 to x1 of di alpha, okay, di alpha of f as a function of x and alpha with respect to x. Okay. Hope that makes sense. Trying to pull up a question where we can actually practice an integral that requires Feynman trick. Let me see here. Can use one of them from either my book or something related. By the way, if you want to learn more about these types of integrals, trust me, there's plenty of more integrals in my book if you're interested. So if you like learning integral methods, either for your classes or for anything else for that matter, or if you like to challenge yourself when it comes to calculus, you can find my book either on Amazon.com or on my website. Okay, there'll be information near the end of this lecture. Any questions so far? All right, so I'm going to continue talking. All right, so we've got this. So let me give you an example problem. Okay. Here's an example. Let me think of one here. Let's say you want to calculate. I don't want to start way too crazy. I want to just, for those of you who are new, to sort of have to go intermediate, then get harder. Either going to look at my book or other references. Just 1 second. Nope. Well, we can do that, maybe. So we do that one. I had a good. Oh, yeah. Yes. I think we're going to look at one of these guys. Yeah. Okay, so let's say we want to calculate this integral here. Okay, let's say I want to integrate sine x. So let's say I want to integrate sine x dx all over x. Okay, so let's say my integral is equal to this. Okay, and my limits of integration will be going from 0 to infinity. I want to make sure that makes sense though. Just give me a sec. All right, so we're going to use this integral right here. Okay, perfect. I'm glad that you guys are you're finding it handy. So yeah, I'm just going to see if this one is doable. Just want to make sure that the limits of integration that I have will make sense at the end of this. Yeah, it's fine. Those limits of integration are fine. Okay, so let's say we want to integrate this. Okay. For those of you who already know, there is no known elementary way of calculating this. You can't use power function. You can't use integration by parts. You can't use substitution. You can't use trig integrals don't work because this is sine x over x. So we have to deal with the x in the bottom. Tables doesn't work. All sorts of things don't work. Okay, even the methods I showed you earlier won't work. So the way to deal with a problem like this is to use the Feynman trick. Okay, now we need to put our parameter alpha in a place such that when I differentiate and then simplify after, I'm able to come out with a clean, beautiful, simple integral to integrate. Okay. So I need to place my alpha somewhere. So let's come up with alpha. I'll say I as a function of alpha is equal to the integral from 0 to infinity. Can you guys guess where my alpha should be placed? Anyone, can you guess where my alpha should be placed in this integral sine x over x? Remember, I want to place it such that when I differentiate both sides with respect to my parameter alpha, I will be able to integrate it after. Anyone have ideas? I want to see your ideas. Okay, so no one has ideas. That's fine. So what we're going to do is I'm going to do this. I'm going to highlight this. I'm going to say sine as a function of alpha x with respect to x all over x. Okay? Take my word for it. I know that sounds not mathematical, but I'm going to explain why in a second. Then it's going to make a lot of logical sense. There's a reason why I placed the alpha there. If I differentiate with respect to alpha, okay? So if I differentiate both sides with respect to alpha, right? So let's say I do that technique now, Feynman trick, right? Well, this is the Feynman trick, right? When I put the alpha in, that's Feynman trick. Now, differentiating under the integral sign is the more precise phrase, right? So if I differentiate both sides, this now becomes I prime, okay? So this is now capital I prime as a function of alpha is equal to d by d alpha, integrate from 0 to infinity of sine of alpha x dx over x, right? Now, what I can do here, you should all know from your very first calculus class that I can interchange the differential operator with the integral. So now it becomes the integral from 0 to infinity of d by d alpha as a function of sine as a function of alpha x all over x with respect to x. Any questions? Yes, yes. That's exactly it. The x comes out. That's why I put the alpha there, because everything else, the x will be like, if I differentiate with respect to alpha, x will be a constant, it gets pulled out, x gets canceled. I'm left with just sine alpha x, and then it becomes somewhat easier to deal with, if that makes sense, right? So yeah, that's right. So what we have now is this. Okay, so I'm going to say integral from 0 to infinity of d by d alpha. This now becomes x by sine of alpha x dx all over x. Okay, and then from here now, it's just going to cancel. This over here is it's going to be the integral. Okay, so it's going to be the integral from 0 to infinity of sine of alpha x dx, and this is equal to my capital, remember this is my capital I prime of alpha. Okay. Now, I'm dealing with this bizarre bugger, sine of alpha x. Remember, I want to be able to integrate. I can integrate this function. It's a simple function to integrate. Okay, integral of sine, right? Sine would be cosine, right? Now it's to be negative cos. So, yeah, integral sine is yeah, negative cos. So it's going to be negative 1 all over alpha. Okay, so negative 1 all over alpha of cosine alpha x bounded from 0 to infinity. I like to put that limit. I don't like to do it that way. I like to say limit as t approaches infinity of, we said cos, I believe, cos of alpha x from 0 to t. Any questions so far? It should be cos alpha x. Yeah, that's right. That's right. Yeah, that's what we're doing. Yep, that's exactly it. Yes. It will also be negative cos, and negative 1 over alpha cos alpha x, right? Because if I do my u sub, u is equal to alpha x, du equals alpha dx. I solve for dx, 1 over alpha 1 over alpha du is dx. I get substituted in. Integral of sine of u, if I were to do that in one step, sine u would be negative cosine u. U is alpha x, so negative 1 over alpha cosine alpha x. Right? Does that make sense? I hope that makes sense. Okay, so we have that part here. Now, the next part is to say that negative 1 over alpha, right? So negative 1 over alpha, taking the limit, right? The highlight my limit here, limit as t approaches infinity of, in brackets, I'll say cosine of alpha t minus cosine of 0. Okay. All right, so we have something like that. Any questions so far on any of this? Any questions? Isn't the term in the integral cos alpha x? Isn't the term in the integral cos alpha x? You said cos alpha x. Yeah. Yeah. But let me show you why it's negative cos, right? Because remember, the derivative of sine is cosine. If I were to integrate integrate cosine, I get like a negative sign. So that means that if I solve for the reverse, for cos would be negative cosine. Is that making sense? I hope that's clicking, right? So it's to be negative cosine. Is that making sense? Okay. When you differentiate, oh, let me get back to your question. Yeah. Wait, but when you differentiate sine of alpha, it goes, yeah, let me explain. So let me just erase this. I'm going to put extra steps here. Oh, good grief. Let me put extra steps. Just 1 second. Yeah, I should have used another extra step or two. Yeah. So let me put to the side here, okay, what it is, right? So d by dx of sine x is cosine x. Okay. Cosine x. So if I integrate both sides, d by dx of sine x equals, and integrating with respect to x, right? So integrate both sides with respect to x. The left-hand side, the derivative integral cancel. Yeah, integrate this side, cos x dx. Then this becomes sine, let's say sine x plus c is equal to the integral of cosine x, right, dx. That will be for that. Okay, derivative of sine is cosine. However, though, if I wanted to figure out what the integral of sine is, okay, I want to figure out the integral of sine, I have to figure out, reverse engineer it. Know what the derivative of cosine is, right? The derivative of cosine, d by dx of cos x is negative sine x, right? Integrate both sides, d by dx cos x equals integral of negative sine x dx. Okay, that cancels. Cosine x equals negative integral sine x dx. Okay, I'm looking for sine x, sine alpha x. If I'm looking for the positive integral sine x, I have to divide both sides by -1. So negative cosine x equals integral sine x dx. Does that make sense? Yeah, yes. Be careful. Yeah, I'm going to clarify certain things here. All right, so yes, let's continue. Okay, so we've had that. Okay, so let's get back to let's get back to it. So I was looking at this integral over here, okay? So I have I, capital I prime of alpha. So this I prime of alpha now. Now remember, I need to do a U substitution on this. Okay, I need to do U sub. Let me just make some room here. Just 1 second, I forgot what time it is. Yeah, so let me just erase this and do a U sub. Okay, so I have to use U substitution on the sign. Okay, so let U equal alpha x. My differential now has to be alpha dx, okay? If I solve for dx, I get 1 over alpha du equals dx, okay? Then I will substitute into my original integral, okay? So I prime of alpha, so capital I prime of alpha, that's the derivative of the integral, okay, as a function of alpha. And then this is equivalent to the integral from 0. What's my limit of integration, though? What should be my limits of integration? Guys know what my limit of integration is. So it'll still be 0 to infinity, looks like. Yeah, 0 to infinity. That's right. 0 to infinity, we substitute it. And then sine, let's see, sine as a function of u, because I want everything in terms of u substitution. So u is alpha x. Dx would have to be replaced with 1 over alpha du. Okay. So now this becomes 1 over alpha. Alpha is a constant. Integral from 0 to infinity. Sine of u du. Okay, so we have that. Integral of sine u du, as I mentioned, is the negative cosine u. So negative 1 over alpha cosine of u. We said, I like to put that limit there. I just love putting limits. Limit as t approaches infinity of cosine of u from 0 to t. Okay. So now I have that. I'm going to use another page here. Let's get to another page. Okay, so now we got another page. So we're going to go to I prime of alpha was negative 1 over alpha, we said. Over alpha, limit. Any questions? Okay, so no questions yet. Good. So make sure you guys are following. Negative 1 over alpha. Just 1 second here. Negative 1 over alpha. 1 over alpha. Limit as t approaches infinity of, I think we said it was cosine of u, cos u, from 0 to t. So now I'm just going to say negative 1 over alpha, limit as t approaches infinity. Now, this is going to become cosine of t, right? Because u, limits of integration for u were cosine of t minus cosine of 0. Okay, cosine of 0. 0 degrees. Okay, so now we have that. Now, what ends up happening, I get negative 1 all over my constant called alpha. Limit as t approaches infinity of cosine of t minus 1. Now, what would I do with this? What should I do with that? What should I do with the cos t minus 1? How would I take care of that? There is a bit of an issue, though. There's a reason why I say that. We get a bit of a something weird. If I take limit as t approaches infinity of cosine of t as t goes on forever, right? Right, as t goes on forever on the graph here, okay? For cosine t, right? Cosine t we know is like this. Okay, that could be a bit problematic, don't you think? As t goes to infinity, cos t goes to what? Yeah, cos t minus 1, can you substitute? No. Can you not evaluate? Here's the thing, though. It's cos t. So as t approaches infinity, cos t approaches infinity. That's going to be a problem. It's like saying our integral is undefined. Cos t, would it be 0? Because it averages out between -1. No. Nope. No, that can't do that. Now, just another inner guy. Can you substitute alpha back in? 1, -1. Potato. You're thinking of, I think you're thinking of a telescoping series of some sort. It looks like you're writing a telescoping series. 1 minus 1 plus 1 minus 1. No, not quite. Nope. However, we have the cos t. Cos t would be a bit of a problem. I am trying to see how we can get out of that situation. Because even for me right now, I'm just saying, what the hell's going on? Okay, so let's see. I've done this before. How did I do it again? Cosine t. Cosine t, where's t goes to infinity? T goes to infinity. If I back substitute something in. Wait a minute. Integrate both sides. If I integrate back, can we integrate yet? Because I want to get I of alpha. If I integrate both sides, I get I of alpha. Integrate that with respect to alpha. Should I integrate now and get I of alpha back? Seems that we've reached a bit of an issue. I'm trying to see how we can get back to how we can get rid of that issue, the cos t minus 1. Just 1 second, guys. Because the cos t minus 1 is a bit of a problem. Replace cos t with something. No, that won't work. No, that doesn't work. No, so it's still going, it's bounded to infinity. Crap. Let me make sure that everything's okay on the previous page here. Yeah, this was fine. Just 1 second. Yeah. Yeah, that's fine. That's fine. Yeah, that's fine. That's fine. That's fine. That's fine. That's fine. What did I say my original function was? We won't use that yet. Later on, we will. That's a bit weird. Alpha t approaches infinity. Do I need a summation of some sort? Cosine t summation. No, I don't need to put a Maclaurin. Do I need a Maclaurin expansion for cos t? Maclaurin power series on cosine t? No, I don't think I need that. No. Yeah, no, I don't need to do that. Cosine t minus 1. How did we end up with this? Help, guys. It seems I'm slightly stuck. I've done this before. Anyone else have any ideas? Any ideas of how to take care of the cos t minus 1 as limit as t approaches infinity? Because so far, that's what the math shows us, is that we're getting some type of a roadblock, right? Because as t, it's very clear, as t approaches infinity, cos t will approach infinity. As t approaches infinity, this is a t-axis, then cos t approaches infinity, but yeah, it's a bit of a problem. If I integrate both sides, because remember, simplify, integrate. Well, I can't integrate yet. I have to get rid of the limit. What else can I do with cos t? Any ideas? Thinking. That's a bit of an issue. Cosine t minus 1, t minus 1 factorize. No, I didn't factorize that. Infinity. Did I say earlier that the limit as cosine of u, let's go back here, sine, yeah, cosine u, 1 over alpha cos u, 0 to t, limit as t approaches infinity, 1 over alpha du, 1 over alpha du is dx. Yeah, that's fine. Yeah, that's fine. I integrated with respect to x, that's completely fine. Yeah, that's fine, Yes, that is fine. Yes, that is fine. Yeah, that's fine. So what the hell is the problem? T is approaching infinity. Bounds and cosine t. Limit as t approaches infinity. Minus 1 to 1. No, I can't use L'Hopital. No, can't use that. Damn it. Why am I stuck? I'm actually stuck on a problem. I hate when this happens. Sorry, guys. I'm just trying to... pull up any theorems from before, because I have too many in my head. Sometimes that's another problem too, when you have too much stuff. Theorems. That's not trying to measure identity. It can't be that. Any theorems? Any theorems? Any theorems? Any theorems? Come on, that doesn't work. Any theorems? That doesn't work either. Nope, that doesn't work. Oh, damn it. Wait, no. So this is wrong. Automatically, it's wrong because we're getting an undefined problem, undefined solution. So that has to be wrong. Okay. So this is wrong. This is wrong. We have to retrace our steps back from the previous page. Sorry about that, guys. Okay, so this is wrong. Let's go back to the previous page. That means that this is wrong. Yeah. Even though the integration is correct, the U substitution is correct, more likely our Feynman trick didn't work here. That's what's causing the problem, because we shouldn't be getting cosine t minus 1. Okay, so having a Feynman trick of saying like sine alpha x doesn't work. Sometimes you're going to have to go through this. You're not going to get the Feynman trick right on the first time sometimes, depending on how annoying the integral is. Okay, sometimes it can look this looks seamless, right? It seemed like that we could have placed the alpha inside of the sine alpha x, but it seems that it's not working. So we have to choose another position to place our alpha or some function with the alpha. Yeah, because sine of alpha x is not working. Any ideas? Any ideas, guys? I think I got it. Okay, yes. The eureka moment, I think I have. Okay, so what we're going to use, I think we're going to do this. Yeah, let me erase this. Erase, erase, erase. Sine of alpha x. So I'm going to do it like this, I think. Because even though it gave us an integral that was easy to integrate, it's still, even though it's easy to integrate, it gave us an undefined answer. So if the problem gives you an integral that's either impossible to solve, or you integrate it and you still get an undefined answer, something's wrong with your Feynman trick. So you have to redefine where you're putting your alpha, reposition it. Okay, so I'm going to say sine x over x, sine x all over x, times e to the alpha x dx. Yeah, this will work. This will work. This should work. And the reason for that is because if I take the integral of e, if I differentiate both sides with respect to alpha, the x will come out, the x and x cancels, then I'm left with the integral of e to the alpha x sine x dx. Then from there, I can use integration by parts twice. And then more likely that I think that will work. Okay, so we're going to do it that way, right? So we're going to do it like this. Okay, so e to the alpha x. Then I'm going to say that capital I prime of alpha is equal to d by the alpha of integral from 0 to infinity of sine x all over x e to the alpha x dx. Okay, like this. Interchange the integral and differential. So integrate from 0 to infinity. D by the alpha sine x all over x e to the alpha x dx. Okay, now that I have this, I integrate from 0 to infinity of d by d alpha. That means the inside here. Okay, sine x over x is treated as a constant, d by d alpha, right? So it's going to be like this. It's going to be, I'm just differentiating this part, sine x over x, the d, this part here. So 1 second, the d by d alpha of e to the alpha x dx. Okay, that makes sense. And then you'll notice from here, this becomes the integral from 0 to infinity sine x over x d by d alpha e to the alpha x. If I differentiate with respect to alpha, the x comes out as a constant. So x e to the alpha x dx. This is left with the integral from 0 to infinity. X gets canceled. E to the alpha x times sine x dx. And this is equal to I prime of alpha. Okay. Let's see if this one works. If placing it, as I said before, if placing the alpha didn't work, right? Like if it immediately gives you an integral that cannot be integrated or gives you an undefined value, it's a good chance that you may need to reposition your alpha in your function or combine it with another function. And the reason why I did e is because of the fact that if you differentiate with respect to alpha as e to the alpha x, the x will come out because x is a constant. When you differentiate with respect to alpha, the x and x gets canceled. So this is a good indication that this is another way to do it. Okay, any questions so far? Any questions? Questions. Okay, so we're continuing, right? So we have this integral. Now, I have this integral here. What I'm going to do is, if I have this integral, I want to be able to solve it. So obviously I need to use not use substitution, integration by parts, if that makes sense. Okay, but before I do that, I'm just going to say this: I prime of alpha. I like to always write like this: limit as t approaches infinity, integrate from 0 to t, e to the alpha x sine x dx. Okay, because I'm approaching infinity, so t approaches infinity. Then I'm going to say let u integration by parts, so e to the alpha x, therefore du now. Okay, my du with respect to x would be alpha. Let me see, that's an alpha, yeah. So it'd be an alpha e to the alpha x dx. dv now is equal to sine x dx. V is equal to integral of sine x is negative cosine x, u times v minus the integral of v du. We're just using the formula, right? This formula here, if you've forgotten, integral of u dv equals uv minus integral v du. Integration by parts, right? All right, so that's what we're going to be using. So this now becomes capital I prime of alpha is equal to the limit as t approaches infinity, okay, as t approaches infinity, and now I'm substituting this integral in for my integration by parts. So u times v, e to the alpha x. Let's see, that's a cosine x, u times v, so minus e to the alpha x cosine x. Yeah, I believe that was, yeah, cosine x. Boundaries from 0 to t minus integral of v du. So that's minus integral v du. So this becomes alpha, let's put an alpha out here, alpha e to the alpha x cosine x dx. Hope you guys are following. Yeah, I mentioned it. I don't know if you heard me or paid attention. I added e to the alpha x. So because here's the thing. With Feynman trick, you have to understand, you either want to place your alpha in the original function in a position such that when you integrate, it's easy to integrate, okay? However, though, in this case, it looked easy to integrate, but we got an undefined value, so that didn't make any sense. So if where you placed it didn't work in the first place, you may need to multiply by a factor of some function quite often, okay? So that's why I multiply by e. Now, the reason why I put the e there is because I noticed that if I take the derivative of e to some function of x, the constant will come out in front of the e. And if I differentiate with respect to alpha, then my x has to come in front. X is a constant, and then it's x divided by x. It's canceled. So that already tells me I'm in the right vicinity. I more likely would be, because the other one also canceled out x. But the thing is, we got an infinity, which was a problem. But here, I also cancel out x. We may have something here that might work. Okay. You're welcome. Just another internet guy. I'm just continuing on here. So yeah, let's get to the next page. Okay, so we got that. Now we got capital I prime. Okay, so capital I prime of alpha. Where were we again? So this was page, let's track. I prime of alpha, where were we? I prime of alpha was limit is equal to limit t approaches infinity. Okay, so t approaches infinity. Okay, so t approaches infinity of e to the alpha x. Yeah, that's nasty. Minus e to the alpha x. And we said that was like a cosine x. t plus alpha integral e to the alpha x as like cosine x, I believe, cosine x dx 0 t. I think we said that. Yeah, okay. Now you can see that this is a cyclical integral. What do I mean it's cyclical? Normally for integration by parts, when you do it, you want to make sure that your newer integral is easier to integrate. Here we don't have that. So we have to integrate again. I think you guys would agree, right? You have to integrate again. So so integration by parts again. So let u equal e to the alpha x du alpha e to the alpha x dx, right? Okay, so we got that. Then over here, that's a du. Well, my du's look good. Then I have my dv. Dv would have to be cosine x dx. So cosine x dx. V has to be the integral of cosine. So it's going to be sine of x. Okay. And then capital I prime of alpha equals limit t approaches infinity, negative e to the alpha x, cosine x 0 to t. Okay. I like when my letters are better. I think when that happens. Cos x plus alpha. Alpha is a constant. Multiply this. Now we're doing integration of parts on this integral here. Okay. This integral right here. So u times v. E the alpha x sine x, boundary from 0. uv will be d. Yeah, 0 to t we said, minus integral from 0 to t, v du. So this becomes the alpha on the outside, e to the alpha x sine x dx bracket. Okay, does that make sense? I hope this is okay. All right, so this is fine. Okay, so this is what we have right now. Then from here, right, I prime of alpha is equal to the limit as t approaches infinity. Yeah, t approaches infinity of minus e to the alpha x cosine x, boundary 0 to t. Okay, 0 to t plus alpha times e to the alpha x sine x 0 t. I should multiply right now. Multiply in the brackets. Yeah, so this is alpha e to the alpha x, alpha e to the alpha x 0 to alpha e to the alpha x sine x 0 to t, minus alpha squared integral from 0 to t of e to the alpha x sine x dx. Okay. So now my capital I prime of alpha is this. Okay. And then what I'm going to do is trying to simplify as much as possible. So I prime of alpha, limit as t approaches infinity, minus e to the alpha x, cosine x, boundary goes from 0 to t. Let's see over here. Actually, no, I can do it right now. I think I should be able to do it. What can I do right now? Yes. Yes, let's do that right now. Yeah, let's do the limits of integration. So e to negative alpha t, cosine t, okay? Minus becomes plus e to the 0, cos 0, okay? Plus alpha e to the t sine t, minus alpha e, minus alpha e to the 0 sine 0, minus alpha squared integral from 0 to t e to the alpha x sine x dx. Any questions? Perfect. Excellent. Thanks, guys. Okay, so we have that. Then from over here, I get I prime of alpha. Okay. Now I'm going to evaluate the limit soon. So just 1 sec. So I'm going to get rid of the t approaches infinity. E to 0 cos 0 is 1. That becomes minus e to the alpha t cosine t plus 1. Okay. Yeah, looks like a plus 1. Alpha e to the t. Yeah, plus alpha e to the t sine t. I need some water here. Just giving lectures, it always dries my mouth. Minus alpha e to 0 is 1. Sine 0 is 0. This goes to 0. And then you're just left with minus alpha squared integral from 0 to t e to the alpha x sine x dx. Okay. Now I'm going to evaluate the limit for each thing here and so forth. Limit as t approaches infinity. Okay. Now, this here, as t goes to infinity, so as t goes to infinity, negative e to the alpha t cosine t approaches something. So as t approaches infinity, negative e to the alpha t. So what happens? As t approaches infinity, minus e to the alpha t cosine t approaches what? Should be approaching 0, I believe. Let's see here. I think it's approaching 0. If we drew a graph, if you have a graph here, normally for exponential decay, this would have been e to the negative x. E to the negative x or e to the negative t would look like this. Minus e to the t. So we know e to the t. Yeah, that goes to 0. That's to go to 0. So this is approaching 0. That's gone. Then I'm left with 1 plus, because it's approaching the asymptote at 0. Alpha e to the, we have 1 plus alpha e to the t sine t. T goes to infinity. T of e to t. It's a 1 there. Yeah, so this would be equal to, let me just rewrite this. We don't need the limits now. So now it's going to be I prime of alpha is equal to 1. 1 plus alpha e to the t sine t. T sine t. T goes to infinity. Let me think here. E to the infinity. E to the infinity sine infinity. Y equals e to the t. T goes to infinity. T goes to infinity. E to the t goes to infinity. T cosine t. I'm going to take care of that in a second. Because right now, this should be gone, I believe. Anyone know how to evaluate this limit, alpha e to the t sine t? Alpha e to the t sine t. Anybody? Alpha e to the t sine t. T is approaching infinity. Make sure everything's okay. Yeah, looks good, looks good. Alpha e to t, alpha e to t. 0, 0, 0. Yeah. E to t goes to infinity. 1 minus alpha squared. I prime was equal to that. So we're going to 0 as well. 0. So this would be 1 minus alpha squared integral from 0 to t e to the alpha x sine x dx, and this is equal to I prime of alpha. Okay. Hope that is good so far. All right, so we have this. This is our integral that we have. Now, we've already integrated this for a second time. We don't need to do it a third time. And let me explain why. I prime of alpha, we calculated on one of the other pages here. I prime of alpha was initially the integral of e to the alpha x sine x dx. So I'm going to equate it. See what I mean? Like, that's the neat part. This integral here, right? This integral right here. Okay, it's from 0 to t e to the alpha x sine x dx is equivalent to I prime of alpha. So I can say that this is the integral from 0 to infinity. I don't need that t now because I got rid of the limits after evaluating. 0 to infinity, 0 to infinity, e to the alpha x sine x dx equals 1 minus alpha squared integral from 0 to infinity, e to the alpha x sine x dx. Okay. All right, so this is what we have now. Okay, I hope you're seeing what we can do with this. There's a reason why I did that. How can we simplify? How can we simplify this integral? Remember, I'm solving for the integral of e to the alpha x sine x dx after the first time of using integration by parts. I don't need to integrate this a second time. Move this over, collect like terms, simplify, solve for the integral. Right, so this now becomes integral from 0 to infinity e to the alpha x sine x dx plus alpha squared integral from 0 to infinity e to the alpha x sine x dx. This is equal to 1, right? Collect like terms, factor out the integral of e to the alpha x sine x dx, 1 plus alpha squared, integrate from 0 to infinity. Yeah. Squared, yeah, exactly. 1 plus alpha squared integrates from 0 to infinity of e to the alpha x sine x dx. This is equal to 1, right? So this is what we have so far. Okay. Right, so we've got this. Okay. Then I want to solve for this integral. Divide both sides by 1 plus alpha squared. So integral from, let me make some more room. Integral from 0 to infinity e to the alpha x sine x dx is equal to 1 divided by 1 plus alpha squared. Okay, so now we've got this. I hope that is making sense. Is this good so far? Hope this is okay. Okay, I just use some ingenuity here. I don't know if it's ingenuity. I just use some creativity. It does require some good intuition to notice that I couldn't integrate us. Usually, you only have to use integration by parts a maximum of 2 times. It won't let you. Usually, you don't need to do a third time. Usually, if you have to do it after a second time and you still hasn't integrated, look for collecting like terms. Left-hand side, I prime of alpha, I noticed was e to the alpha x sine x dx. Right-hand side is the same thing. Rearrange, collect like terms, factor out, and solve for this integral. Now, I have all of this, but this integral was originally I prime of alpha, which is equal to 1 all over 1 plus alpha squared. And the evidence for that is on the other page. 1 second. Yeah, over here. I prime of alpha is the integral, the improper integral 0 to infinity e the alpha x sine x dx. So I can equate it. So I prime of alpha is 1 all over 1 plus alpha squared. Now we are in a good spot, I would say, because we finally integrated. So we have the derivative of our integral as a function of alpha equal to this. Okay. So from that part here, okay, I still need to get rid of that sign there. Let me see here. Yeah. So what I want to do now is I want to be able to get rid of the derivative. Because remember, the next part of Feynman trick or integrating differentiating under the integral sign is you want to integrate one last time, right? So remember, at first, step one, you always take the derivative. You take, step one is find the parameter. Position your parameter somewhere in the integral, right? That's Feynman trick, such that it's integrable. Then after that, differentiate both sides with respect to alpha. Once you've done all that, clean it up. Then you may have to deal with an integral because you want to be able to solve for that derivative, the derivative of the integral. Clean that up. But since you have the derivative of the integral, right, you want to be able to integrate, get rid of the I prime of alpha, right? So I prime, I'd have to integrate both sides. So integrate. And when I mean integrate, it's an indefinite integral. So I prime of alpha with respect to alpha. And then the same thing on the other side, integral of d alpha divided by 1 plus alpha squared plus c. All right, I hope that is making sense. All right, so then from here, what we want to do is, I have this integral, okay? This integral right here can be solved easily. Well, the left-hand side is I of alpha. The right-hand side, the integral of d alpha all over 1 plus alpha squared. How do we integrate this? I know you guys seen this integral before. Think of the integral of dx all over 1 plus x squared. What is the integral of dx over 1 plus x squared? Anybody know? Anybody know the integral of dx over 1 plus x squared? Okay, so it's arctan, right? Arctangent. Arctangent of alpha plus c. Okay, that's what we have here. So I of alpha is equal to arctangent of alpha plus c. Right? Integral of d alpha all over 1 plus alpha squared is arctangent. Arctangent of alpha. That's the formula if you don't know. You should know it from elementary calculus if you're taking it at some point. Okay. So we have this guy right here. Now, remember, the original integral that we were wanting to calculate was this, the integral from 0 to infinity sine x all over x dx. We want to know what that is. We can calculate that, but we need to get a definite answer because this is a definite integral, limits of integration here. So we need to get an answer, like a number. We can't leave it like this. This is an indefinite value because we have an arbitrary constant. Okay. Anyone have any ideas of what we can do? Hint, hint. We need to solve for the arbitrary constant by using initial boundary conditions. Anybody know? Just want to see in the chat before I get back to the whiteboard. Anybody know? Okay, so I'll go back to it. So I of alpha was this. But remember, since I of alpha, careful now, I of alpha was defined way earlier. What I mean by that is, let's go back to what we defined I of alpha as. I said I of alpha was the integral from 0 to infinity of sine x all over x, e to the alpha x. I multiplied by a factor of e to some power of alpha x dx. Okay. Right, I of alpha, when I used Feynman trick, I put I as a function of alpha equal to an integral as a product of e to the alpha x dx. I needed this in order to get somewhere, a factor of e to the alpha x. So I'm going to substitute Well, I'm not going to substitute it yet, but what I'm going to do is I have I of alpha now. So that's good. However, before substituting it into that equation, I need, what's it called? Initial values or boundary conditions. So in order to get C, I need to know what I of alpha is, and I need to know what my alpha value is. Okay. If that makes sense. So what I'm going to do is I'm going to evaluate I of 0. Okay. So I of 0. So did I use I of 0? Let me see here. I of 0 should be fine. Yes, so alpha is 0. Okay, so I'm going to use initial value of I of 0 and see what that spits out. We get integral from 0 to infinity sine x all over x, e to the 0 is 1. And that gives me integral from 0 to infinity of sine x all over x dx. Okay, that's I of 0. Now, if I did I of 1, so I'll make sure you guys are following. Hope you guys are following so far. Okay, I know this is a bit tricky. As long as you follow and you have a strong background in integral calculus, you should be fine. Okay, so let's continue. So we have integral from 0 to infinity of sine x over x dx. Okay. Should I have used I of 0? Let me see if I did I of 0, alpha 0, 1. So either 0 or 1, sine x over x, integral of sine x over x dx. That gives us back to what we were looking for. I want to simplify this somehow to get an actual answer. Oh, wait a minute. No, I of 0. Then I'll do I of... I of 0. I of infinity. Alpha goes to infinity. Alpha goes to the negative infinity. E to the negative infinity would be 0. That integral collapses to 0. 0 is equal to... See, that doesn't help. Does it? Infinity. 0. Arctangent infinity. Oh, yes. Okay, so we know I of 0 is this integral. Integral from 0 to infinity of sine x over x dx. Okay? That doesn't help us much. We want an actual value. Okay, so let's do I of infinity. Okay, so when alpha approaches infinity in reality. Okay, so this equals the integral from 0 to infinity of sine x all over x e to the alpha x. Alpha is approaching infinity, right? Dx e to the infinity. Infinity is equal negative infinity. Okay, so negative infinity. Otherwise, you want to make sure that your alpha that you're choosing for your initial boundary conditions gives you sensible answers. If I did e to the infinity, right, that would have been a problem. E to the infinity, we know, goes on forever, right? As x approaches infinity, e to the x would approach infinity, and then infinity times infinity is infinity, and that doesn't give us any answer for a definite value for C. I'm going to do as x approaches, like having it negative infinity, right? So e to the negative infinity would be a decreasing function, decaying function. So that means that it's approaching 0. So this goes to 0, right? E negative infinity is 0. So I of negative infinity is 0. Okay. So I'm going to evaluate at I of negative infinity. I of negative infinity is 0. So I can substitute that in here. So 0 is equal to arctangent of, now remember, I inputted alpha was negative infinity. So every alpha, I'm putting negative infinity, right? So this was, when I meant 0, I meant I of negative infinity. I'll write it like this first. So I'm substituting arctangent of negative, yeah, we said arctangent negative infinity. Okay, arctangent negative infinity plus C. We know that arctangent of any infinity is pi over 2, right? Automatically it has to be pi over 2, right? Because you have tangents, the tan function. This is why I like to draw a lot, because in math, because, and I specify that as one of my approach to problem solving is using visual spatial skills and critical thinking as my two, main points like to specialize, try to bring home when it comes to solving math problems, right? So let's say you have a function like this. Sorry about that, it's not there. At every pi over 2, tan x is undefined, right? Pi over 2, 3 pi over 2, so forth, right? You have stuff like this, right? So it's like, so I know if pi over 2 is undefined, right, then the inverse tan of undefined has to be pi over 2. So this is now gives me pi over 2 plus c. I have negative infinity 0, right? Because we said that. Therefore, c is equal to negative pi over 2. Well, if c is equal to negative pi over 2, so c is negative pi over 2. Okay. Let's see here. Where was it? It's only like one more step. I'm just getting lost because I have so much stuff here. Yeah, because c was negative pi over 2. C is negative pi over 2. Just 1 sec. I can't find it. I have trying to find my stuff here. Yeah, c is negative pi over 2. Therefore, I. So what's had happened here actually is that my integral from 0 to infinity of sine x dx all over x should be pi over 2 if you input c. Yeah, pi over 2. And that is our solution. Any questions? That was a nasty one with Feynman trick. But it was definitely fun. Okay, I hope you understood what happened there. Okay, I hope you enjoyed it. We talked about special functions, beta and gamma functions. We talked about using Feynman trick. One last thing before I get going is the last 10 minutes, 10, 15 minutes will be about what was on the list. I was going to talk about something interesting here. Just 1 second. Yes, contour integration. Any of you have any understanding of how to do a contour? Actually, before doing the contour, I'm going to give you guys this for homework if you want to try it. All right, so if you want to try this Feynman trick problem, so there'll be another page here. So homework problem, just to remind you, this was initially not in my plan for homework. I wanted you guys to do it during class, but maybe we actually don't have enough time, actually. This will take forever. Integral, yeah, let's do this problem. Integral from 0 to infinity, e to the negative alpha x. Here I've already placed the parameter. You don't have to figure out where it is. 1 plus x dx. This is a homework problem. Okay, so that's for homework. So for anyone who wants to try this, this will be a homework problem. I was going to assign it during the lesson, but I don't think we have enough people and enough time to do it. Okay, so just let me know if you want to try this problem. This will be a challenge problem. Okay. All right. So we got this. And then finally, okay, so now that we have all that, we're also going to talk about one last thing. Contour integration. Okay, have any of you guys done any contour, have heard of contour integration by any chance? Any of you? Any of you done any contour integration? Let me know if you've done contour integration in the chat. Thumbs up, thumbs down, yes, no, give me something. Contour integration. Okay, so I'm assuming no. I'm going to give this lasting 5-10 minutes in the chat. Okay, so we're going to be looking at contour integration. Now, here's the thing. As I said, this was office hours for people who have already seen, mainly seen my live shows or lectures from the last videos. So for those new people who either, in the case if you not knowing, you may know what I did last lecture, but didn't see it, and you may have no idea what contour integration is, you may need to look at my last 2 videos. Okay, the last 2 videos is on contour, the theory of contour integration, because when it comes to math, you need to know the theory. If you don't know the theory, the rest of the stuff ain't going to make sense. Okay, you're not going to understand how I'm doing the problems. Okay, and you can either learn the theory from either watching my last live shows, okay, and or you know, asking for a one-on-one meeting with me as well on the side. You can get it's even better because then you get like extra specialized help. Okay, so I do tutoring lessons as well for undergraduate students, and yes, and or you can also purchase my book, which will guide you through how to do contour integration if you're going to be stuck. Because as I mentioned, this is going to be a little bit tricky. You want to understand what I'm doing right now. Okay, so you have to refer either to some references or past videos, or you can contact me directly for a one-on-one meeting, or you can go through, you can purchase my book, and I'll talk about that in a sec. Okay, so in the moment, we're going to look at this problem. Okay, this was a problem that was supposed to be left as a challenge problem from the people from last time. They didn't show up today, I guess they're retired or whatever, but this was the problem from last time. Okay, and the challenge problem was to take the integral from 0 to infinity of log x dx all over x squared plus 1. Okay, so this would require a contour. Okay, and I wanted them to solve it, but since they didn't show up, I have new people, and I feel like, oh no, I'm going through something that you may not understand. I hate when this happens. I'm going to go gently on it. You don't have to understand what I'm saying at this point on. However, though, I do want you guys to read up on contour integration. Okay, so here is some of it. Okay, what you do with contour integration is you specify a certain type of geometry that will not hit branch points, and it has to do with complex numbers. Contour integration has to do with taking. You can have an integral in the real numbers, but then you're going to transpose it into the complex numbers and apply theorems of contour integration that will be able to simplify a very difficult, normally tricky integral in the real numbers, but you transpose it into complex numbers, specify a certain geometry based on what the complex contour is. And then after all those theorems, you should be able to find an answer. So for the one I was talking about, log x over x squared plus 1, right? It looks something like this, okay? I'm not going to talk about it, but you define a contour, a keyhole type of contour, okay? Find using definitions, right? So there's a lot of definitions. I use 3 definitions of contour integration here. Hope you find this cool. Put something in the chat if you find it cool. You want to learn more? Okay. And the contour is breaking up into subsets of contours. What I mean is subset of paths that you have to add up. So if you've taken multivariable calculus, you will understand, or are taking multivariable calculus, you will understand contour integration. It's not as, I mean, it can be complicated, but it's not as complicated as long as you've seen what a line integral is and you have to parameterize everything. Okay, so that's what this is. It's just parameterization on a complex plane. That's what contour integration is. Okay, so contour integration is just that. Okay, so there's different definitions, stuff like that. You'll be probably familiar with this, adding up different paths. This is paths, adding different paths of contours. Okay, so that's what we do here. Okay, that's all we're doing. And also another definition is the path reversal. Okay, so if you take a related property, reversing the direction of the path, it changes the sign of the integral, right? So instead of going counterclockwise is negative clockwise, right? Solution continued. We just add up all the different paths. We had 4 different paths because our contour was traced like this, right? This is what we call a keyhole contour. We use keyhole contours when we have to deal with, quite often, logarithms and/or functions raised to a fractional value because they give us multi-valued solutions. Okay, so it's strongly recommended to use a keyhole contour. This is how they look like. Okay, so going around, round. Okay, and you can see that on the outside we have a path gamma. The whole path, the whole circular region is gamma. C1 is the upper arc. Inside here, the parallel lines, there's C2. Okay, parallel lines C2. Both parallel lines are C2. Okay, C3 is the inner circle. The inner circle here is C2. The outer circle is gamma. The inner circle and the outer circle will cancel because their path direction is different. One is going like this, the other one's going counterclockwise. Right? So one is going clockwise, C3 is going clockwise, gamma is going counterclockwise, so they cancel in the addition. And then we also have C4, the lower arc here. And then I use the theorem to add up all the contours because we have multiple paths here. We add up each contour integral. Okay, f of z dz, multiple times, n number of times, depending on how many contours we have. Okay, and then I use definition 2, apply this, I add, subtract everything. Then I do that, I simplify, I use the residue theorem. As I said, you won't understand unless you see my other lectures. Okay, so the last two videos will make sense. And then from here we find the singularities. F of z is log z, where z equals 1. Singularities mean what can be undefined in the denominator of a complex number. Okay, z is plus or minus I. Substitute into residue calculation formulas. Get this for z equals I, z equals negative I. I get that. What did we say here? Yes, we did that. Page 3, is it? Page 4. And as you can see here, some more theorems. And what ends up happening after the residue theorem is our actual integral should be 0. Okay. And I think that will be it for today. Okay. So yeah, I recommend either looking at the past videos, right? But if you want to understand like contour integration, that's another mathematical integral method that can help you in your courses. Okay. I'm going to see if anything else I had on my list here today. Nope, that wasn't it. Let me see anything else. Okay, that wasn't it. Nope. Let me see. So that's it for tonight. I hope you guys enjoyed it. Okay, we covered a lot of stuff. But yeah, I think that will be it for tonight. Like and subscribe. I hope you like and subscribe because it will help the channel keep running. If tonight helped you understand special functions, Feynman trick, residue calculus. Well, I don't know how much of you understood residue calculus. That's with the complex numbers. I was expecting some of the other guys from last time to come back. That's fine if you didn't. Residue calculus and everything we did, as I said, comes directly from my book, Advanced Integration Techniques. Okay. So yes. Okay, so Advanced Integration Techniques, which is available on Amazon or on my website. Okay. I'm going to put the description in the link of this live show right after. Like and subscribe again. And if you want mentorship or help with advanced math, physics courses, engineering, you can apply at STEM1online.com, and that'll be it. All right. So have a good night, guys, and I'll see you next time. By the way, my schedule: Sundays, Wednesdays, and Fridays are the live shows. Okay. Have a good one, guys. Bye-bye.